So how should we find this integral? A complex monster demonic looking integral. So for that we need a little bit of complex analysis. Recall that e to the power of ix is the same thing as Euler's identity, that is cosine x plus I sine x. So what I'm going to do is I'm going to replace this one here from 0 to pi over 2 x times cosine x plus I sine x over sine x dx. And if I expand this integral, it's going to be x cotangent x plus integral from 0 to pi over 2 of I sine x over sine x dx. I forgot x here, so what I'm gonna do, we can cancel out these sine x's. Now, now it's gonna become the integral from 0 to pi over 2 of x cotangent x plus, so the integral from 0 to pi over 2 of xi dx is going to be x squared I 0 to pi over 2, which is I pi squared over 8. So plus I pi squared over 8. Now we're just left with this integral, so we gotta find the real part of this integral to find out the answer to it. For this, I'm gonna use the Feynman's technique, and for that, I'm gonna call f of a to be the integral from 0 to pi over 2 of arc tan of a tan x over tangent x. I can write cotan x as x cotan x as x over tan x, and if my f of a is 1, it's gonna yield x because arc tan of tan x is x. So what I'm gonna do, I'm going to take the derivative of both sides with respect to a to remove this tan x in the denominator and make this integral solvable. So f prime of a is the integral from 0 to pi over 2 of partial a of arc tan of a tan x over tan x dx plus 0 because the derivative of a constant is 0. My f prime of a is therefore the integral from 0 to pi over 2 of 1 over tan x. With the chain rule, I'm going to multiply it again by tan x times 1 over 1 plus 8 squared tan squared x dx. These two tan x's are going to cancel out, and I'm left with f prime of a, the integral from 0 to pi over 2 of 1 over 1 plus 8 squared tan squared x dx. I'm going to do a change in variable, but before that I'm going to multiply and divide both sides of this equation by secant squared x. So secant squared x dx. I'm allowed to multiply by 1 as long as I'm just multiplying and dividing. So I'm going to say t equals tan x and dt equals secant squared x dx. Did you see why I did that for? I wanted to connect this secant x to tan x somehow, and if my t is pi over 2 and my tan x is infinity, so I gotta change the bounds of f prime of a from 0 to infinity of 1 over 1 plus 8 squared t squared times dt is going to be here, and the secant squared x in the denominator, it can be simplified with 1 plus tan squared x, which is 1 plus t squared. So 1 plus t squared. Now what I'm gonna do, I'm gonna do a fraction decomposition. I'm gonna say f prime, I'm gonna say these two fractions are a over 1 plus 8 squared t squared plus b divided by 1 plus t squared. And it's going to be 1 plus t squared plus b times 1 plus a squared t squared. A plus at squared plus b squared at squared. If I collect the like terms, at squared plus ba squared t squared plus a plus b, this whole thing should be equal to 1 because our whole thing here, is equal to 1. So I'm going to factor out t squared. It's going to be a plus ba squared plus a plus b equals to 1. This t squared should go away, thus I can conclude a plus ba squared equals 0, and a equals negative ba squared. Thus, this thing has a coefficient of 1, so this a plus b should be equal to 1. So a plus b equals to 1. And if I substitute a here, it's going to be negative ba squared plus b equals to 1, which is b minus ba squared equals to 1. Factoring out b, I'm going to get 1 minus a squared equals to 1. Thus, b equals 1 over 1 minus a squared. So, thus my a is going to be negative a squared over 1 minus a squared. And if I write my integral again, it's going to be integral from 0 to infinity of, so it's going to be negative a squared over 1 minus a squared, 1 plus a squared t squared plus 1 over 1 plus t squared 1 minus a squared dt. So, I'm gonna zoom in again. So, now it's better. So my f prime of a, I can factor out this 1 over 1 minus a squared out, and the integral is going to be 0 to infinity of 1 over 1 plus t squared minus a squared over 1 minus a squared, 1 plus a squared t squared dt. And if I integrate both sides of this equation, now I can integrate this thing here. So I can say f prime of a equals 1 over 1 minus a squared of arc tan of t, this thing is arc tan of t, minus a arc tan of at. This thing is a arc tan of at. You can check it by taking the derivative of that. So this is from 0 to infinity, and obviously this zero bound is going to go to 0, and arc tan of infinity is pi over 2, and arc tan of at is also pi over 2. Thus 1 over 1 minus a squared is pi over 2 minus a pi over 2, and we got 1 over 1 minus a squared times pi over 2 of 1 minus a, and I can use the difference of squares here to cancel out and make it more simplified. Thus it is pi over 2 times 1 over 1 plus a, so this is f prime of a. Thus if I integrate both sides of this equation with respect to a, dA, I'm gonna get f of a to be pi over 2 ln of 1 plus a plus c, some constant of integration. Now recall my f prime of a, my f of a was the integral from 0 to pi over 2 of x cotangent x it was arc tan of a tan x over tan x dx plus I pi squared over 8, that are imaginary part. So equals to pi over 2 ln of 1 plus a plus c, some constant of integration. Thus I can say that my constant of integration is I pi squared over 8 if my my a approaches 0. If you use the limit, you're gonna find it out. So my f of a is pi over 2 ln of 1 plus a plus I pi squared over 8. And my f of 1, because I was looking for f of 1, is going to be pi over 2 ln 2 plus I pi squared over 8. And this is our complex integral solved with a little bit of complex analysis. And this is our integral result that is in imaginary plane defined. So this is how we should solve the integrals that are complex using the Feynman's technique. This was pretty much of a long work, but I hope you've understood it very well. Please like and subscribe to my channel. If you have any questions, please let me know in the comments. I'm gonna read every single comment, and I will see you next video.